Camille Cornett, and this is Lab 5 for Physics 2211. The purpose of this lab is to find the falling motion of the slinky and to construct a model in GlowScript. The motion was tracked using Tracker, and the video I used was from Veritasium. The results, the model used two calculations, one for after the bottom of the slinky fell and one for before, and overall the model moderately accurately predicted the motion of the falling slinky. Some physics problems and principles used in this lab were from Newton's second law, force equals mass times acceleration, or the change in momentum over the change in time. The position update formula was used when plotting the position of the slinky, and the velocity update formula was also used. The force of drag was used for after the slinky started to fall, and it is listed above. Also, the force of gravity and the force of the spring. These are the calibrations I made in Tracker to accurately track data. I used a height of 1.75 meters for the man on the left, and I plotted my axis as shown. The initial conditions were the slinky had a mass of 0.218 kilograms, an initial position of 6.57 e to the negative 2 in the x dimension, 0.481 in the y dimension, and 0 in the z direction. The initial velocity was 0 as the slinky was not moving. These are the initial conditions for the code. As you saw above, the velocity, the mass, and the position are listed. The drag constant b was used through checking and guessing, and this is a number that I ended up with. This is the code I used to track the slinky falling before the bottom of the slinky fell. So as you can see, the force of tension of the slinky and the force of work done by the slinky are inverse. So in the model, the slinky doesn't move. F net is 0. Then the slinky is plotted. So up until this point, in the y direction, the bottom of the slinky does not move. For the second part of tracking the slinky's motion, the F net is not 0. So the force of drag and the work done by gravity are not equal to 0 when added together. The work done by gravity is greater, so the slinky ends up falling. This is where we see on the graph, which we'll see on the next slide, that the slinky in the y direction has begun to fall. The graph on the left is taken from GlowScript, and it is very linear. It doesn't have many discrepancies, and the one on the right was taken from the observed data. If we look, we can see that both models are moderately similar. There's some discrepancies, but overall we can say that the GlowScript predicted model is quite accurate. Some potential may include the error in the drag constant, which was found by guessing and checking, or human error in the tracker or any other means not previously mentioned. What does it mean? Why is the slinky's motion different than the typical falling object? That's because in the beginning, when the bottom of the slinky doesn't fall, that's because the tension of the slinky is directly acting against gravity. So the bottom of the slinky doesn't begin to fall until after the tension force in the slinky is 0. What if the bottom of the slinky was heavier? The answer is it depends. As long as the slinky is either long enough or has a large enough spring constant so that the tension is directly inverse to the gravitational force, the weight will remain stationary until the tension force in the spring is 0. And finally, the bottom of the slinky does stay stationary in the model as it does in the video.